Good afternoon, ladies and gentlemen. I'm Abhay from the marketing department of EDS Technologies, and today I'll be your host for the webinar. First and foremost, I would like to thank each and every one of you for taking your time out and joining this webinar. Without further ado, let's begin this today's webinar on delivering superior performance, decreasing customer anxiety, and assuring vehicle safety in electric vehicles. So today's focus will be on the structural analysis and thermal management of electric vehicle batteries. So I would like to begin this webinar by giving a short introduction about our company EDS Technologies. EDS Technologies was incorporated in 1994 to focus on providing PLM solutions, implementation, and support. We are the largest PLM and engineering solutions provider in India and also platinum partner to Dassault Systems. We have served more than 2,000 customers across India and operate in 9 locations across India, with our headquarters being at Bangalore. We also have strategic partnerships with world leaders like EOS for additive manufacturing, Human Solutions for ergonomic solutions, Technia for ensuring product data quality, for military simulation and training needs of aerospace and defense industry. We have partnered with Prestiges and MAC for visual simulation solutions. With respect to EDA solutions, we closely work with Synopsys, and for GIS, we have a partnership with Esri. We also have signed up with Festo for Industry 4.0 solutions for the academic institutions. We have a dedicated sales, support, marketing, and customer satisfaction teams to address customers' PLM business and support requirements. Coming to the EV industry in particular, we are engaged with multiple EV manufacturers in India. In terms of solutions, we support them for battery engineering, body structure engineering, charging infrastructure, electric powertrain, interior and exterior trims, and electrical wiring harness. In today's webinar, our speaker will be Mr. Onkar Madhekar. Onkar is currently working as the application engineer in EDS Technologies, and he is looking after the Simulia business for Western region. He has been associated with clients across various industry verticals, including transportation and mobility, industrial equipment, life sciences, etc. Prior joining EDS Technologies, he was working with Altair Engineering and Ashok Leyland. Onkar has completed Masters in Design Engineering and Bachelor's in Mechanical Engineering. So before handing it over to Mr. Onkar, I just want to say that we'll be taking up the question and Q&A session after the delivery of the webinar. However, we will be accepting queries through the question box, which each of the participant can type in, which will be addressed post Onkar's delivery. Hope you have an exciting and knowledgeable session. Over to you, Onkar.
Okay, great. Thank you. Thank you so much for this fantastic introduction. I would appreciate it. So today's agenda is firstly we'll start with what is current Indian EV market, then followed by battery design considerations. Then what are the cell parameters? We will just focus on a couple of important ones, followed by battery cell engineering. Again, into that cell design, thermoelectrical losses, strength, stiffness, durability, aspects of the same, and battery module and pack engineering. Again, into that design, thermal management, like cell strength, stiffness, durability, safety, and thermoelectrical losses we'll try to see. So as per recent data available with us, we have crossed 1 million plus EVs sale in last 12 months from Feb 2022 to Jan 23. See, EV includes two-wheelers, three-wheeler passenger, three-wheeler cargo, four-wheeler, buses, and other segments also, which is a very promising figure, I would say. So EVs accounted for almost 5% in 2022 of overall automobile sales. So till 31st of July 2021, there were only 380 EV manufacturers in India. With the increasing adoption of electric vehicles in the landscape, This number is expected to increase further. The models approved by FAME2 by Government of India along with their manufacturers are 39 for two-wheeler, 81 for three-wheeler, 19 for four-wheeler. Recent update, what we have received so far is one of our first kinds of deposits of up to 5.9 million tons out of 98 million tons of lithium deposits are found in Jammu Kashmir's Riyasi district. Thanks to India's Ministry of Mines and Geological Survey of India for these rare earth metal deposits. Now definitely we can adopt greener solutions. If we deep dive into the cell chemistries of these lithium ion cell batteries, there are more than 10 plus types of lithium ion batteries available. I suppose many of you might be aware of it. So various chemistries of lithium ion cells, including LCO, NMC, LFP are preferred choices. LCO is nothing but lithium cobalt oxide, is used for portable electronics. NMC is lithium nickel manganese cobalt oxide, which is preferred in EVs. And LFP is lithium iron phosphate, which is a preferred choice for low range EVs and energy storage systems. To deep dive into all the parameters, we must understand what are the cell parameters. Firstly is internal cell resistance. So there are two methods to measure internal cell resistance of the cell, ACIR and DCIR. ACIR uses AC current that is passed through the cell and voltage response of the cell, whereas DCIR measures the DC resistance characteristics of the cell. SOC is nothing but a state of charge. It is measurement of the energy available in cell at a specific point and is expressed as percentage. It is important requirement to estimate SOC because it can protect the battery and improve the battery life. In generic also, it is considered 100% when the cell is fully charged and is considered 0% when it is fully discharged. It can also allow the application to make rational control strategies to save energy, of course, depending upon the applications. Types of SOC estimation includes direct measurement, bookkeeping estimation. Next one is SOH, which is state of health. It plays vital role to understand when the cell is nearing to its end of life, EOL, which is actually a parameters which we will see in the subsequent slide discussion. It is also called the retention capacity of the battery. It is the measure of existing capacity of the cell as compared to the capacity of the cell when it was brand new. Lithium ion cells come in two grades, as we know that first one is EV and second one is ESS. EV grade cells are called power cells and ESS grade cells are called as energy cells. Next one is gravimetric energy density. It is also known as specific energy, which is capacity of the or nothing but a parameter of the battery, which tells the energy storing capacity of the same per kilogram. Next one is end of life. When it comes to using any kind of battery technology, it is the point of which the battery can continue to work to the level of performance that is accepted, because later on we'll throw it away or we'll think of any other option. So the performance factors include range or backup time, maybe discharge power, charging speed, etc. So after studying all these parameters, let us see what are the important battery design considerations. First one is SOC, again what we have just seen, which is nothing but a behavior of the battery as it is temperature dependent. Different insulators will address the issue, so they will sustain longer, because which is our utmost purpose. In battery chemistry, As we know that lithium ion cell is a type of battery where lithium ion moves from cathode to anode during the charging phase and anode to cathode during the discharging phase. During this process, electrons are released from anode to supply energy to the application. So basically, it's an anode, cathode, and electrolyte solution mixture. So to provide a way to analyze the different chemistries and how they encompass and provide longer cell charge. In efficiency, it is important characteristics, because even if you try increasing it by 5%, it will definitely reduce your heat dissipation, that is heat generated by 5%. It can be improved by different strategies. In safety, which is of utmost priority, there are many workflows to predict when the battery will start to fail and maybe internal short also. We'll see what is internal short and all in the subsequent slides. In aging, how fast the battery is aging and how is end of life behavior of the battery, and meet the higher target of the maximum life. Next one is temperature spread. Battery aging heavily depends on the temperatures. Now already we know this. So if you are operating the equipment for a longer period of time, you are reducing the lifetime of the battery. And if you have a part of the battery in higher temperature and a part of battery in low temperature, a part of the battery in higher temperature tends to lose life faster than the one which is in cooler condition, and it results in imbalance of the battery. That's why the spread is critically important. Next one is durability. We have to make sure that the battery cell and the device or the structure it is sitting in is durable, because and it is definitely to prevent the we must understand when it is getting failed before the whole device fails. So the battery should not be the center of all this. In sustainability and recycling, rechargeable batteries, as we know, is a very common now, but only very few percentage of them are recycled, and it is becoming more and more of a concern for government for environmental safety issues. So they are coming up with different regulations. We know in AIS 156, and there are a couple of amendments of the same. So they can track batteries stage. If you are designing the same from a concept phase itself and related to this particular parameters, we will be able to sustain and recycle the ecosystem of the battery for sure. So we'll start with battery cell engineering. I hope you can see from molecular chemistry, we'll jump into cells, again from cells to module and pack, and from pack again into the vehicle. So in the first part, as you can see, number one, battery cell design is for 2D or 3D, whichever, depending upon the application, we can do that. The next one is thermoelectrical losses. It is for the efficiency of the battery and how the temperature affects the battery. Strength, stiffness, durability. It is the thermomechanical behavior of the battery. Next one is safety. Here, it will focus on abuse conditions, how the battery will perform in accident, drop, so as to avoid the future failure. Next one is model order reduction, which is nothing but the structural model reduction to reduce computation time and cost. So we can create the detailed 3D parameterized cell geometry and mesh the same with the all functional requirements. This was just an introduction of that cell, how that can be generated and given by the meshed model also in the second part. Now I'm playing a video to get how that cell design can be done. A small example is shown through the video. So we'll be able to do primary CAD design, benefit of the parameterized model is that whatever changes you are doing in the CAD are getting reflected. Definitely with the help of platform, which you can see on the screen. Departmental communication will also become easy. So you will have clear design of what is the status of the activity. You can see on the top screen, top left corner, CATIA part design was there. So we can leverage CAD. Now you can see Simulia structural model creation and relevant applications of the same. So meshing is done. Cut section is getting checked. So the same model from Abacus is exported to platform. It's a jelly roll model. We can take the input file in platform. So as stated, input file can be checked. Units can also be changed sometime. So connections can also be provided. You can see in model creation of Simulia application. So model building was carried out in that. Here it's for processing, where input file for missing functionalities can be given. So analysis is now getting checked. We are running the model on the platform, or opening the same can be also possible if the model is solved. And finally, the post-processing phase. Post-processing can be done on a backer screen as well as in the platform. You can check which are the areas where electric potential is maximum. We can again modify the same. Current density was checked. So temperature contour is getting checked now. So The next is thermoelectrical losses. Here we'll assess this type of next type of losses. So where you charge or discharge the battery, the chemical reaction happening inside the battery will release the heat and to some percent absorb also the heat, but definitely released is more, and some part of the battery like terminals will pass currents. So that's why, and considering many other scenarios, we'll have to study thermoelectrical losses and how that creates thermal stresses. This will determine battery efficiency and thermal management or heat generated due to the battery. Some solutions may offer only thermal or other choices, but in here we have coupled solution of thermoelectrical and mechanical as well. So benefits here we will get here are prediction of the energy losses in the battery cell considering all the relevant physics in coupled environment, using the flexible collaborative environment of the 3D experience platform where we can connect the geometry and simulation modeling, execute on-premise or on cloud, manage all relevant data at one place, enhance 3D experience simulation power by approach, where mixed native and external meshes to feed the analysis with the most suitable meshes can be checked. We can easily switch between the application, so pre and post processing or solving can be done, and definitely best in class abacus solver will be there running behind. So in strength, stiffness and durability, we know that stress depends upon SOC. This is with respect to electrical primarily front, SOC and SOH of the battery. So age of the battery can be considered over swelling when subjected to charging and discharging. Goal is to check mechanical integrity of the battery in different work conditions and to check the same during in-service performance. You can see stress plots, strain plots, temperature and density plots are there on the screen. So these are the different loads from mechanical front, which are nothing but the abusive scenarios where axial, radial, bending, and static or dynamic impacts are checked. So we are able to measure damage internally to the core of component, which is the most important part, and how cells will perform with different loads. So predicting deformation and damage is one of the progress in this case. Now to showcase all these functionalities, which is nothing but a testing part, I'm playing another video. So prepared geometry can be called here, or we can directly create the same on the platform. So cut section is getting checked from CAD and as well as mesh front. As already stated, from CAD to simulation, each and everything can be checked on the same screen, but with the change of application. So axial compression analysis is getting checked now. You can see bottom section is fixed, which is clamped, and from the top the load is applied. It's for 3-point bending analysis. So two ends are clamped, and from one, that is which is on the top, displacement is applied. and impact case. So boundary conditions and other parameters you can see on the feature manager, which is available on the screen right now. And these are the results of that impact simulation. Results of the bending simulation. So we can focus on the areas also, particular sections, as you can see on the screen, which is zoomed in. Von Mises stresses are getting checked now. Side compression tests, which was carried earlier. Proceeding further, so reduced order homogenized cell modules. This process allows us to build a cell model that is structurally and thermally equivalent to the original one, very detailed cell module. And we are able to reduce the node count because there is no single cell, it's a pack, and again multiple packs are there in the battery. So this allows us to analyze thousands of cells in a pack more efficiently. You can see mass is also the same, but the nodes are reduced from 1.3 million to 5,000. So benefits here are assess structural integrity and safety of the battery cell in virtual environment. We can cover linear, non-linear behavior, minimum modeling effort to resolve multi-physical phenomena from various different types of simulation. Let's move further for battery module and pack engineering. Till this point, what we have seen was with respect to cell. Now we are diving into pack. So like cell simulation, we can append the same to the pack level as well. With the proper design iteration, pack can be designed. Effective cooling strategies can be adopted in thermal management. Safety issues can be addressed as well. We'll look into the points in subsequent slides. Here in detailed design, we have the structure where all the batteries are fitting in. So different types of arrangement can be explored depending upon the type of application, depending upon the complexity where it is getting fitted, and many more permutations and combinations. In thermal management, we are looking at the air cooling of the cylindrical cells, and similar design happen in other power tools as well, where there is a housing. Inside housing, there is a cell arrangement you can see, and venting as well, inlet and outlet. And they are defined in such a way that air should reach to the drive components or necessary ones, which will carry heat. One of this type of cooling analysis is that to cool the batteries uniformly and efficiently. As a parametric model, which we discussed earlier, we could do the study of distance between the different cells. The first one is original one, which we started with. Second one is tightly packed, and the last one is loosely packed. When the gap is smaller, flow speed is faster. Flow speed is kind of faster, combustion coefficient is as it is higher. Air may be hotter because of that. So we need to define the optimal gap balancing airflow through the ducts and the temperature distribution. So forced air cooling and liquid cooling are compared in this case. In air cooling, Airflow is designed from the bottom to cool the battery. So external flow analysis, you can see temperature plot. And the second one is where the coolant is running inside the channel. The channel has coolant plate. The whole channel had a contact to the battery. So the one is external flow and one is the internal flow, which can be addressed. So you have the choice to pick from the different scenarios, definitely. So in strength, stiffness, and durability, we are interested in finding out multiple scenarios from pack level, including the cells, as the cells would contribute partially in the process. So different loads, materials need to be analyzed to meet the expected performance with minimal effort, minimum material and manufacturing costs. In this case, bead optimization was performed. It was done to increase the casing stiffness. You can see without beads and with beads. Without beads, it was 203 Hertz, and with beads, it's 233 Hertz. Deformations on the whole pack level are also available. You can see step 1, which was pretension. Strain values were 1.6 into 10 to the power minus 4. In the second step, it was swelling, and in the third step, which was aging, where state of health was 0.8 and strain values were checked, BB section was considered. So similar to the previous cases, safety analysis can also be performed. We are assessing the battery, the whole structure in this case. Different test scenarios are shown in the subsequent slides. So drop, crush, top or side penetrations are common scenarios and can predict the damage caused by all of these different impacts. You may hit a small stone that hit the, you can imagine the scenario where the stone is hit to the car, and when you have a battery pack placed there, you want to access the damage and make sure the battery is not damaged and make some corrections if there is any, and sometimes make cause from crash event also. After this event, you don't want your cell or pack to damage too much and cause fire. You can analyze these scenarios. You can see. So another safety concern is thermal runaway, which is there in this slide as well as in the next slide. It can be caused by the internal short or some type of mechanical or thermal electrical abuse like overcharging that can trigger the battery system, or wrong way. A battery thermal runaway is the situation that for any of the above mentioned reason, part of the battery reach a critical temperature of the material, and once this temperature is reached, they'll start to decompose and have an accelerating reaction, and definitely it will release huge amount of heat, and if this heat is not properly mitigated, it will conduct nearby material, and nearby material will reach critical temperature like a chain reaction, and then propagate through the whole cell, and by the end eventually breakdown of the cell and battery and destroy the same. So with the simulation, we can predict the thermal runaway, which is shown in subsequent slide also. So we have to come up with a mitigation strategy to control such failure. So as stated, this is how the propagation takes place from one to next, and the chain reaction follows. So key is to check the damage, to link the damage to a particular cell by proper insulation in case of investigation purpose. So internal short, which is the next case, that happens when the separator layer has been compressed and is thin enough to start to have some electrical current flow through and can cause inside a battery. It is very dangerous because a short have a lot of current to flow through. So you will generate a lot of heat if not controlled. Overheating will happen and then it may turn into fire. So we are able to closely predict the force and punch displacement and corresponding to when short will happen. We can predict when the stroke will happen under what kind of scenario. Now we know how it happened. We can modify the design to mitigate such kind of issues. The last point is thermoelectrical losses. Because of the reduced model, we can simulate complex scenarios like thermoelectrical ones, which will reduce the total time as there are multiple packs. Above showcased is one of the pack level of the example. This one is liquid cooling pack, which holds many cells, while it's cooled by a coolant pipe now wrapping around the cells. And we are able to predict the thermoelectrical losses of the cell and temperature of the cell and at different locations of the pad, and you are able to predict the average cell temperature with maximum and minimum temperature. You can come out with the design to reduce the cell temperature difference and the spread what we have seen in previous slides, so that the whole pack is more balanced. Now the part of the pack is overheated while the other part is probably cool. This will cause the imbalance which we have seen and that overheating one. So part of this pad will fail early and you can improve the cooling efficiency. So to conclude the same, we can do multiple types of simulations from a cell level to a pack level. And again, there are many aspects definitely connected to that, which probably will be seen later. I think that's all from my side.
So I would like to thank the audience for staying through the webinar. Please stay tuned for more informative sessions surrounding electric vehicles. We'll be bringing you more such informative sessions. Before closing, I would also like to request the audience to fill up the feedback form. So I would like to thank once again Mr. Onkar and all the audience for their participation in this webinar. Thank you.